Once free charge carriers are generated, they can recombine again. But how does this recombination work? What are the possible recombination mechanisms in a solar cell? And what is the recombination rate of each mechanism? These questions will be answered in the following two videos. First, we will identify 3 different recombination processes. Subsequently, we will discuss the physics of the underlying mechanisms of each recombination process. And finally, we will discuss the recombination rate of each process and see how to calculate them. Before we dive into the recombination mechanisms, let's briefly recap what recombination means. As we discussed in the previous video, recombination is the annihilation of free charge carriers. There are 3 different recombination processes: radiative, Meitner-Auger, and Shockley-Reed-Hall recombination. Meitner-Auger recombination in literature is often only called Auger recombination, but it turns out that Lise Meitner also reported this effect around the same time as Pierre Auger. We will therefore refer to this process as Meitner-Auger recombination. In this video, we will discuss radiative recombination and Meitner-Auger recombination only, while Shockley-Reed-Hall recombination will be discussed in the next video. Let's start with radiative recombination. In radiative recombination, the energy of the electron is emitted as a photon after recombination. The energy of this photon is slightly larger than the energy of the band gap of the semiconductor material. For the purpose of this video, we will state that the photon energy is equal to the band gap energy. Radiative recombination is in fact the mechanism that light-emitting diodes or LEDs utilize. Radiative recombination is very significant in direct bandgap semiconductors, but relatively rare in indirect bandgap semiconductors like crystalline silicon. The recombination rate for radiative recombination is given by the following formula. This rate is proportional to the concentration of electrons, N, in the conduction band and of holes, P, in the valence band. The equilibrium concentrations N0 and P0 need to be subtracted, which leaves us with the net recombination rate. Beta in this equation is a proportionality factor and is material dependent. Depending on the illumination conditions and on material parameters, this expression can be simplified. For example, let's look at an N-type semiconductor under low-level injection. Here, the change in the free electron concentration, delta N, is negligible compared to the total electron concentration, N. Additionally, the concentration of holes is much lower than the concentration of electrons, as electrons are the majority carriers and holes are the minority carriers in this N-type material. This leads to the following expression, where the term between parentheses is effectively the excess free hole concentration. This leaves us with the radiative recombination rate for N-type semiconductors under low-level injection. A similar derivation can be applied to P-type semiconductors, resulting in the following equation where N and P are interchanged. The next process through which excited charge carriers can recombine is Meitner-Auger recombination. Meitner-Auger recombination is a 3-particle process. The momentum and energy of the recombining hole and electron are transferred to another electron or hole. This third particle is excited deeper into the respective band and relaxes again by a process which is called thermalization. In this thermalization process, this free electron in essence loses some of its energy in interaction with the crystal lattice. When the third particle is an electron, it is an electron-electron hole process, which is abbreviated as EEH. If the third particle is a hole, then obviously it is an electron-hole process, which will be abbreviated as EHH. Minor Auger recombination strongly depends on the charge carrier concentration, since a higher concentration increases the probability that these three carriers can interact in this way. Therefore, the recombination rate of the EEH process is given by the following equation. The recombination rate is proportional to the square of the electron concentration N, since 2 electrons are involved in the process. The concentration of holes, P, is also important due to the fact that 1 hole is necessary for Meitner-Auger recombination to take place. Cn is a proportionality constant. For the EHH process, the hole concentration is squared, while the electron concentration is not, and Cp is the proportionality constant for EHH Meitner-Auger recombination. By combining both processes, the recombination rate of Meitner-Auger recombination is obtained. We will now simplify the recombination rate for N and P-type materials. If we look at a strongly doped N-type material under low-level injection, we can assume that the electron concentration N is equal to the donor concentration Nd, and that the hole concentration P is negligible compared to the electron concentration N. This leads to a Meitner-Auger recombination rate that's dominated by the EEH process. Therefore, this simplified expression can be used to calculate the Meitner-Auger recombination rate for N-type materials. The same derivation can be performed for P-type materials, resulting in the following expression. In this case, the recombination rate is proportional to the acceptor concentration, Na, squared, and to the electron concentration, N. In summary, we have seen that we can distinguish 3 recombination processes. The mechanisms underlying radiative and Meitner-Auger recombination were discussed, and we now understand their recombination rates. The most important recombination mechanism for silicon-based solar cells, Shockley-Reed hole recombination, will be discussed in the next video.